Okay, we're going to get started here. Thank you everyone for joining us for Planning for Disaster, Stainless Steel Resilient Design, brought to you by AIA provider, the International Molybdenum Association, MOA, and co-sponsored by the Nickel Institute. Both are trade associations who sponsor research and provide independent technical information related to molybdenum and nickel-containing materials. Couple of housekeeping things. Please save any questions for a Q&A session at the end of the webinar. We're going to save 10 minutes for that at the end. Also, if you're seeking AIA continuing education credit or a certificate of completion, please note that you need to be on the webinar for at least 45 minutes and ideally the entire time. Otherwise, we would not be able to provide you either that credit or a certificate of completion. Okay. Also, heads up, I just posted a link in the chat. We have an additional webinar November 8th at 7 a.m. and 12 p.m. Eastern Standard Time. And that is going to be an introduction to stainless steel finishes and alloy specification. So our speaker today is Ms. Catherine Houska. Catherine is an internationally renowned expert in architectural and structural metals. Today's presentation is all about resilient design. Catherine is the chair of ASTM E60-80 General Sustainability and also a member of the E54 Homeland Security and E50-07 Climate Change, which are all developing resilient design standards. So she is key in a lot of the guiding policy here. She is also on the ASCE 370 and 313 and ASCE 8 committees and contributed to AISC DG 27. Catherine has also published over 200 publications, and we are very pleased to have her to present this webinar today. So I'm going to turn it over to Catherine now, and thank you so much.
Thank you, Carly, for that wonderful introduction. Hello, everyone. I'm glad that you could join. I'm hoping that we don't have the technical problems that we had earlier today, since they're doing some line work outside my house. So since you've already gotten the introductory information, I did want to mention the presentation is copyrighted, so you can't use anything within it without the permission of the Nickel Institute and MOA. Everything that I say today is guidance for your decision-making process. We do not provide recommendations. We will steer you toward specifications that can be very helpful, though, as you work on these issues. Our learning objectives. We will talk about the difference between resilience and sustainability and how they relate to one another, and the characteristics that make stainless steel an excellent choice relative to other metals. We'll talk about some human-caused and natural disasters and how stainless steel is being used to provide a more sustainable and resilient solution to them. We'll also talk about some of the new and revised stainless steel structural design resources and some new ASTM standards that should be extremely helpful in your work. So this is a great picture to show a house, a design that was both sustainable and resilient. You can't claim that materials are sustainable if the buildings don't last. And clearly it was resilient to withstood a hurricane. And ideally, that's what we want. We don't want to create waste. The most commonly used definition for sustainable development is the United Nations definition, meeting the needs of the present without compromising the ability of future generations to meet their own needs. This is a bridge. It was the first duplex stainless steel vehicular bridge in the world on an island off the coast of Spain, a highly corrosive location, one where bringing materials in is challenging and very expensive. So they needed something that would actually last, unlike the prior bridges. So examples of sustainable development include energy reduction or alternative sources, of course, human health and safety and welfare, the reduction in resource use, water and materials. We want it to be reusable or recyclable, renewable. We want to minimize water loss and also make sure the materials can last the life of the building, which is part of why ASTM developed the most widely used standard for assessing the life cycle of buildings and structures. We also want to avoid emissions that can be problematic inside and toxic runoff outside. I have a separate presentation on sustainability that goes into that in more depth. But that's not our focus today. We're talking about resilience, and there are often misconceptions about the differences between them. In the United States, every agency has their own definition for resilience. The UN has its own. And from what I understand, the situation that we have among government agencies in the United States also has occurred throughout governments elsewhere in the world. So ASTM E60, my subcommittee, is developing a standard that will define resilient design for the first time in an international standard. There are other standards on resilience that have been developed, and I will send you to some of those as well. So as we talk about resilience, we're talking about withstanding accidental and deliberate impacts, whether it's blast or fire, climate change, and all that brings in terms of flooding and drought and landslides and high winds and fire, earthquakes, terrorism, any other event that is not related to the basic functionality of that building or structure. So sustainability and resilience are different. There is, however, overlap. For example, with sustainability, we're focused on energy reduction. With resilience, we would want multiple energy sources. Energy independence is the middle ground. One of the other areas of, where there's overlap is having materials that last the life of the building and are capable and are also resilient, capable of withstanding whatever might occur in that environment. So multiple characteristics have to be considered as you're assessing a resilient design. Most systems are made from multiple materials. Within that system, one or more may be deliberately intended to fail, while the rest may be intended to stay in place to retain structural integrity, for example. But the goal is always to make sure that that system can be rapidly repaired or replaced so that the building or structure or whatever it might be, community, can be brought back to its normal function as quickly as possible. Corrosion during normal use can weaken that structure. So that has to be considered. And, whatever that might be, you want to make sure that what you had on day one is what you have 10, 20, 30 years down the road when that 100-year event may occur. You also must consider that there can be multiple events occurring at the same time. So during the recent hurricane in Texas and Superstorm Sandy and other events like this around the world, we've not only had high winds and flooding, but also fires that had to somehow be contained when they might be hard to reach. Superstorm Sandy certainly provided that example of all that can happen. And this is what the city looked like. You can see from the flooding map what different types of storm surges, what different levels could do in terms of flooding the city. They not only had flooding with some areas, like some of the parts of the subway system being immersed for extended periods of time, but they had impact damage from floating dumpsters and fires that could not be contained. There was significant long-term infrastructure damage and inadequate housing. So there were many problems beyond what immediately happened that were long-term. And the city is in the process of making it more secure, putting up flood barriers. So when we plan for resilience, this is the classic graphic. At the point of the natural disaster, you want the system to be fully functional. When that disaster happens, we know that there will be a drop in performance. The goal is to be able to have as rapid a recovery as possible. The acceptable drop in performance is dependent on what that system does and how critical it may be to the functionality of the community, the building, whatever it may be. And that may, retaining a higher level of functionality and reducing that recovery time could mean spending more money in the short term to save far more in the long term. As I mentioned, simultaneous incidents are fairly common. A chemical plant fire occurred during a Texas hurricane where there was significant flooding. So the characteristics of material systems, at least the critical structural materials, are impact resistance, blast resistance, seismic performance. There should be good corrosion resistance to whatever is occurring in that environment or might happen during a period where corrections to the system have to be made to restore them. And of course, fire resistance. So as we compare steels, carbon steel has the least corrosion resistance, the least ductility and energy absorption, and weldability. As we go up in alloy content and expense to alloy steel, things get better. If you really need excellent corrosion performance, and there are a wide range of performance with stainless steel, then you want to go with stainless, as well as energy absorption and ductility, and it has good weldability too. All of these things vary with the alloy family and the specific alloy, making identification of specific stainless steel critical. Another aspect of corrosion resistance in particular is when carbon steel corrodes. If you've applied a coating but nobody has maintained it, then you get rapid uniform thickness loss without protection. and that can adversely affect performance. Stainless steel instead corrodes by pitting. And even if you happen to have pitting through the thickness of the stainless steel, you may still have adequate structural integrity for it to perform its role in the case of resilient design. Since I wasn't sure of the background of everybody who would join this call, I did want to provide a quick overview of the range of corrosion resistance levels that are possible with stainless steel, because I too often see stainless steel on drawings or in specifications. You can predict the corrosion resistance of the stainless steel based on chemistry. This is a general ranking. It's not true for, not valid in the order shown for all applications, but it gives you a general feeling for level of corrosion resistance. The higher the number, the more corrosion resistant the stainless steel. So that's, more chromium, more molybdenum, more nitrogen, all increase the corrosion resistance. Well, nickel helps us with welding and impact resistance, among other things. So here you can see the precipitation hardened stainless steels have the lowest PRE and the lowest corrosion resistance. We have a step upward with 304. Then we have the lean duplexes in 316, around 25. Alloy in 2205 is at 35. So again, a big jump up. 2205 is becoming far more popular, and the duplexes are in all of the new structural specifications or revisions that are in process. And we can go all the way up to the 40s. Stainless steels that can be immersed in seawater without corrosion or aggressive process streams. There are a variety of things that have to be considered as you're looking at the longevity of materials, pollution, salt exposure, weather conditions, maintenance, and aspects of design that can also facilitate accelerated corrosion. This is the US coastal deposition map. 60% of the US population, 60% of the global population live in a coastal zone. As you can see, the darker colors, the darker kind of a burnt orange color is indicative of areas that have significant chloride deposition. There are misconceptions that salts are only present a short distance from the coast, and that's simply not the case. There's similar maps for Europe, Oceania, and other countries. So please do look at that if you're working on a project. The other primary source of salts is de-icing. 70% of the US population is in an area with at least some de-icing. The study in Illinois found that de-icing salts traveled at least 1.2 miles from roads and were found in Chicago up to the 59th floor. I have documented de-icing salts 2 miles downwind from a highway. So they have to be considered as well. Any source of salt must be considered. There is a lot of corrosion data out there from all over the world, not just for metals, but for other materials, documenting its rate of deterioration. The South African data has, you can see the different exposure levels with the more severe marine exposures as you go to the right. And that has a direct effect on the corrosion rate. And that could be used to predict how long a material will last. I've used the SMACNA Architectural Sheet Metal Manual, and I've shown the typical roof thickness. I multiplied the average annual corrosion rate for New York City, Curie Beach on the Carolina coast, Durban Bluff in South Africa, and in any location where at 30 years we've lost at least a third of the thickness, then we have to assume that we have perforation. And that will also, of course, affect, the overall performance in a structural application as well. You may or may not be aware that AISC 360 and 303 were published in late 2021. They were, 370 and 313 were published in late 2021. These are a specification for structural stainless steel for buildings or anything loaded like a building. And it covers anything that is hot rolled or hot processed in some way or welded. Not the light gauge structural sections. We also have ASCE 8 is in revision. We're hoping that it will be published this year. It has not been updated in 20 years. So it was really out of date. Duplex stainless steels have been added to ASCE 8. And we've revised which other austenitic stainless steels are included. AISC Design Guide 27, which was the prior guidance that was available for larger structural sections, has also been revised. We have a much larger and more comprehensive design guide to assist you with either of these publications. So here are the covers. If anybody is a member, you can download these for free. They are critical resources to have. Hopefully, we will shortly have ASCE 8 out. 370 covers standard design, tension, compression, flexure, shear, various other loading conditions, mechanical and welded connections, fire resistance, fabrication and erection. It doesn't cover seismic design. Of course, the stainless steel has been used in seismic design, but there wasn't enough data compiled at the point when we were ready to publish to add that section. It will be in the next version. The stainless steels that are covered in 370 and ASCE 8 are the austenitics and duplexes for all structural forms. And then the precipitation hardened fasteners and tension bars. We did not include the precipitation hardened alloys for any product form other than tension bars and fasteners. Additionally, in 370, we require that you assess various types of corrosion that can occur that could have a significant effect on grade choice, alloy choice, and provide a checklist in the commentary so that you know what information is needed to then speak with a specialist in stainless steel corrosion if necessary. Design Guide 27 has additional information. When it's a relatively straightforward choice, we want you to be able to simply go forward with that. But when you speak to someone, we want you to have all the data handy so that there are no misunderstandings. Fire and thermal radiation resistance is critical for so many applications where resilience is required. And not just buildings. This is the Mont Blanc Tunnel, which was closed for 3 years after a fire as the result of an accident. The strength and the stiffness retention are critical. Whether we're talking about barriers like roofing or curtain wall, doors, structural sections. And I should note that you'll see from looking at the data that stainless steel doesn't always have to be insulated. But let me share some more information with you. Sorry, I just realized I was not sharing my sound.
And 4 co-sponsors commissioned Darkem Engineering to carry out a series of fire tests on a standard component, a cable ladder, in aluminium, GRP, carbon steel and stainless steel. The ladder was loaded to simulate working conditions. Aluminium was unable to meet any of the test criteria. In this fire withstand test, it collapsed in 26 seconds. The GRP suffered total collapse in 30 seconds of the fire withstand test. Smoke and fume emission were also noted during the test.
GRP is FRP.
The galvanized carbon steel withstood the heat for the full 5 minutes of the test. However, zinc globules were observed dropping during the test, a potential additional hazard. Stainless steel satisfied all the criteria, and at the sponsor's request, the test was continued until the gas supply ran out, during which time the average flame temperature exceeded 900 degrees centigrade for 30 minutes and 1000 degrees for 14 minutes. Deflection was measured after 45 minutes and was only 80.5 millimeters, compared with 166.5 millimeters deflection of galvanized. In the test designed to measure conduction through walls, aluminium collapsed on the fire side after 1 minute 8 seconds. The remains still exposed on the fire side permitted the test to continue until temperature stability was reached on the cold side. This occurred after 37 minutes, with web temperatures of 152 degrees centigrade and 134 degrees centigrade being recorded. By contrast, the stainless steel withstood the test well, and after 90 minutes, web temperatures on the cold side had stabilized at 80 degrees centigrade and 58 degrees centigrade. To assess the...
So the data for that test, which was conducted over 30 years ago, as the result of a North Shore fire platform, is summarized on this slide. Of course, the aluminum and fiberglass failed quickly. That's not surprising because they're low temperature melting materials. The stainless steel and galvanized steel passed. The stainless steel test, this was a 5-minute test. The stainless steel was continued to be tested for 45 minutes until the gas ran out. And despite that added test time, its deflection was half that of the galvanized steel. So this was the starting point for research on stainless steel performance and fire. And a great deal more research has been done since. So at a high level summary, this shows you the strength retention of aluminum, carbon steel, duplex, and austenitic stainless steels. You can see that the strength of the stainless steels drops off at the lower temperatures relative to carbon steel, but once we are above 600 degrees Celsius or 1,112 degrees Fahrenheit, the austenitic stainless steel is better than carbon steel. And that's specifically molybdenum-containing austenitic stainless steels, like type 316, because the molybdenum does provide an advantage. For stiffness retention, stainless steels as a whole are better. And this this difference can be critical in design because it could mean the difference between something remaining standing and functional, even if you've had a strength decline. And so this is part of why stainless steel for lower temperature fires doesn't need fire protection. You do need to consider the thermal expansion and the thermal conductivity of all the materials in the system. And I did want to point out that these numbers are different for the austenitic and duplex stainless steels. It's critical when you're combining materials in fire to know what those values are and to design for them. You want to make sure that the fire door is open if those are stainless steel, but your structural framing is carbon steel, for example. When we look at the stress strain graphs for the metals we're talking about, you can see carbon steel has that defined yield point. The stainless steels don't, neither does aluminum. But we have a, there's some differences here because of some significant differences in terms of what this means for design of structures. And I'm going to delve into that a bit more deeply. As we carry the stress strain curves all the way out to failure, then you can see that the area under the duplex and austenitic stainless steel curves is much larger than that for aluminum or carbon steel. That is an indication of the intrinsic ability to absorb energy. Aluminum and carbon steel are nowhere close to stainless steel. It's a result of strain hardening and the excellent ductility of stainless steel. And this shows it a bit more graphically. You can see what those areas are under the curves. So the stainless steels are always going to be better in terms of energy absorption and ductility. This was a demonstration building that was built in Japan to get stainless steel into the structural design codes. The half of the building structural sections were stainless steel and half carbon steel. I happened to be there right after the big 1995 earthquake in Osaka that did so much damage. And the building had zero damage. I took a picture of the stainless steel structural sections, and you can see they're perfectly fine. The carbon steel was as well. There have been many designs that have used stainless steel for seismic applications, including this church in Italy, which was an Arab design. When we switch to the Q&A and you see my screen background, you'll see the Golden Gate Bridge. The 2205 is going to be used for the seismic retrofits for it once the funding comes through. So stainless steel can be a big help with seismic design. Another area is preserving water. In Europe and Asia, stainless steel tanks and water lines, including underground water lines and those in buildings, are far more common. They can withstand that cyclic loading that happens in seismic zones. If you have a seismic event and you don't have water, you can't fight fires, and you don't have safe drinking water for those affected. So it is critical to have stainless steel for both. I wanted to talk a bit about blast and impact with resistant curtain wall design. I'm showing an image of a glass curtain wall. and then a stainless steel panel being impacted by truck. Various metals have been used for structural glass framing or for curtain wall for that matter. But as I've already showed you, there's a huge difference in the ability to absorb energy. Additionally, I mean, it's important to note with that stainless steel curtain wall, if your outer panel is stainless steel, but you've used something with less ability to absorb energy, like aluminum or carbon steel behind it, then your whole system is limited by that structural material. So if you need the maximum impact resistance or blast resistance, the whole system, or fire resistance, the whole system has to be stainless steel. I also wanted to show you the weld performance. Austenitic have no ductile to brittle transition. They are ductile down to cryogenic temperatures. And if properly welded, you don't see a difference in the weld performance. The same is true with duplexes as well. They will perform welded or not. The same, whether they're welded or not. And they're similar to carbon steels in terms of performance. Here are some applications where weld impact toughness and the performance of the stainless steel are critical. The passenger rail vehicles globally that are most able to withstand impact are what's standard in the Americas and parts of Asia and some parts of Europe. And those all have austenitic stainless steels for the outer skin and for the structural framing. They can absorb significantly more energy than the aluminum designs or the carbon steel designs without tearing apart, which is much safer for passengers. Stainless steel fencing is the best energy absorption with minimal maintenance. Several of the World Trade Center buildings in New York have 2205 structural sections at the first floor level for holding the glass in place. 2205 has double the strength of type 316. And of course, you can see stainless steel bollards there from the prior slides. Hope you understand that it's not just because of its corrosion resistance. It can withstand far more impact than a painted carbon steel bollard. And this will give you some idea. This is carbon steel reinforced concrete. We're dropping the French dropped a 700 kilogram ball on top of it. This gives you the best view. As you can clearly see, not only did the concrete crumble, but the carbon steel failed. This was avalanche wall work, but it's equally applicable to security barriers. And here is stainless steel. Whoops, let me go forward. I ended up with carbon steel again. Okay, here's the stainless steel. Yes, the concrete crumbled right under the ball, but the stainless steel reinforcement did not break. So it is clearly the best choice. Stainless steel is being used for some concrete slab connections in seismic zones. It also provides impact and blast resistant building, as well as barrier and security walls. It's being used for toll booth, security, government buildings, industrial facilities. It's another example of resilience provided by stainless steel. The U.S. Federal Emergency Management Association requires stainless steel wire to hold tile and slate in place on roofs. If these are not secured, they can become very dangerous flying projectiles, and you don't have to worry about the wire corroding away and not being functional during a high wind event. This is an image of a masonry wall that failed during a seismic event in Australia. You can see the galvanized wire had corroded away. Stainless steel is preferred, particularly type 316 if there's any salt exposure, both for systems that anchor existing walls and for new walls. There is a lot of data about performance in soil environments. Stainless steel is the best choice. The type of soil will determine which type of stainless steel you really need. Aluminum and carbon steel are not at all suitable. They will fail in soil. Cast iron can provide reasonable life as long as there are no chlorides or very low chlorides. But with the increased use of de-icing salt, we're seeing waterline and gas line failures because there's salt now in the soil. This is a company in San Francisco that's been in business for several generations, 3 that I'm aware of. The grandfather had 50 plus years ago had been required to use stainless steel as a ground anchor for walls near a dam. In the intervening years, the family went to using triple protected carbon steel. But when they went back to do remedial work or make changes in these walls, they were finding that it had begun to deteriorate after 15 years. After they were asked to do some work related to a change in the wall, this 50-year-old wall that their grandfather had worked on, they saw that the unprotected stainless steel had no significant corrosion. They did a cost comparison. Triple protecting carbon steel is expensive, and it turned out that they could use bare stainless steel and reduce cost and have a better wall in a seismic zone. Another example of galvanized steel failing in soil, if you were to Google vehicle skewered by guardrail, you will be amazed at how many pages and pages of images you will find. It's because that galvanized steel that's holding the guardrail in place corrodes, and then there's nothing to hold it in place. There's a great deal of data on the performance of stainless steel and other metals in seawater and brackish water. You'll note there is no 304 or 316 on this graph. Neither one of them is appropriate for brackish or seawater. 304 and 904L and 2205 can be used in brackish water, but you're not going to get the long-term performance that you would if you go to a more corrosion-resistant stainless steel. So the Franklin Delano Roosevelt Memorial that was built in New York City, which had a grand opening in 2012, had a 100-year storm surge design requirement. I was involved with this project, and when I learned that meant that the entire island could be submerged in brackish to seawater for days, I discouraged the use of 316, and we instead used 2205. The most visible part of that choice were the handrails. After the storm, Superstorm Sandy, which went through about within a month, there was debris all over the island. The handrails were fine. There was no corrosion on them. New York City is doing a great deal to protect the city from future flooding. I mentioned that they're putting storm barriers around the low-lying areas, but they have also, within the subway system, created customized systems that can block off the entrances to the subway, which are shown in the top left. The handrails can come apart and the waterproof doors close over the entrances. On the South Ferry subway station, which is at the tip of Manhattan and most prone to flooding, and a very busy station. That's 2205 duplex stainless steel, very heavy glass, and there is a barrier door that comes up to seal that entrance. There are, of course, other types of flood prevention systems. If you use galvanized steel or aluminum and they're sitting there waiting to be used, you have to consider how much corrosion might occur over time and whether or not they're going to be functional. There are a variety of resources that I encourage you to take a look at during planning. There's a brand new, literally right off the presses, ASTM E54 Homeland Security Standard. This is based on the NIST Community Resilience Planning Guide for Buildings and Infrastructure Systems that came out, I think, 5 or 6 years ago. And it's taken several years of work to get to where we are, but it was just published. So if you want to know the latest standard, get a copy of E3350. It is now available. ASTM E60, my subcommittee has a standard that is going to define resilient design that is very near passage. I am hoping by the end of the week we will know that it is passed. That has been a collaborative effort to cover all aspects of resilient design, not just those related to homeland security issues. We've had the support of many government agencies as well and professional organizations in its development. Additionally, there is RELY, which is the RELY Collaborative, which is built into USGBC LEED with some pilot points. It's really intended for next generation, completely in a greenfield development, as opposed to these other standards, which are geared more towards a new building or structure in the community, or protecting the community as a whole. If you need technical help, then the Nickel Institute makes it very easy to send an inquiry. And I believe the link has been provided in chat. AMOA does provide technical assistance too. On AMOA's website, you can find a download of a stainless steel library. It has over 550 PDFs covering every topic that you might want. The website also has technical resource pages that go into additional depth or tie together those resources.